Whether it's the water coming out of your kitchen tap or the air rushing past a jumbo jet, the way fluids move, it's all governed by just a handful of really elegant principles. It doesn't matter if we're talking about a simple garden hose or a massive hydroelectric dam. So today, we're going to dive in and uncover those secrets.
So let's kick things off with a kind of wild question. You've got a regular garden hose, right? We've all done this. You put your thumb over the end and the water just shoots out. But how high could it really go? I mean, could you, theoretically, spray water over a 10-story building? It sounds completely nuts, but physics, well, it has a very, very surprising answer. And to figure it out, we have to start with the most fundamental rule that every single fluid has to obey.
And that one rule, the one that is absolutely unbreakable when it comes to fluid motion, is the conservation of mass.
Okay, that definition sounds super technical. I get it. But the idea behind it is incredibly simple. You can't just create or destroy matter out of thin air. For any space you want to look at, what engineers call a control volume, the amount of stuff flowing in minus the stuff flowing out has to equal the change in the stuff you've stored inside. It's really no different from balancing your bank account.
Now, this one simple rule gives us two basic kinds of flow. First up, you've got steady flow. Think of our garden hose. The amount of water going in one end is the same as the amount coming out the other. The mass of water inside the hose itself just stays constant. But then you have unsteady flow, like when you're filling up a bathtub. Water's flowing in, but nothing's flowing out, so the total mass of water inside the tub keeps increasing over time. For our hose problem, we're squarely in the steady flow camp. All right, with that rule tucked in our back pocket, we can finally introduce the beautiful, elegant equation that's going to solve our hose mystery. It's called the Bernoulli equation, and it is the absolute key to understanding how fluids trade pressure for speed and height. But, and this is a big but, it only works in a perfect world, a world with absolutely no friction.
So what is this equation really saying? Well, it's telling us that for a bit of fluid moving along a path, its total mechanical energy is always constant. It's basically conservation of energy, but specifically for fluids. This means the different kinds of energy inside the fluid can morph into one another. Pressure can become speed, speed can become height, but their total sum never ever changes.
So let's break that down. A moving fluid has three types of energy. First, there's flow energy, which is basically the energy it has from the pressure that's pushing it along. Then you have kinetic energy. That's the energy of its pure motion, its speed. And finally, you have potential energy, which it has because of its height or elevation. Bernoulli's equation shows us that these three are in this constant, beautiful dance, always trading places with each other.
So, back to the hose. When you put your thumb over the nozzle, you shrink the area, and all that flow energy from the pressure has nowhere to go, except to convert into kinetic energy, into pure speed. Point that jet upwards, and all that speed starts converting into potential energy, into height. So, using the pressure from a typical city water main, what does Bernoulli's perfect world equation predict? A jaw-dropping 40.8 meters. Let that sink in. That is taller than a 10-story building.
But Bernoulli's equation actually hints at something even deeper. It shows us that pressure isn't just one simple thing. And if we can understand the different types of pressure, we can pull off some amazing engineering feats. Like, say, figuring out exactly how fast an airplane is flying through the sky. Okay, so there are three main types to know. First, you've got static pressure. This is the actual true pressure of the fluid itself, kind of like its internal energy. Then there's dynamic pressure. This pressure only exists because the fluid is moving. It's the pressure of motion. Now, if you take that moving fluid and bring it to a complete stop, all of its dynamic pressure gets converted back into static pressure. That combined total, that's what we call stagnation pressure. And here is just a brilliant application of that idea. Airplanes use a little device called a pitot tube that points straight into the wind. It has a tiny hole that brings the oncoming air to a dead stop, which allows it to measure the stagnation pressure. By then comparing that to the static pressure measured on the side of the aircraft, the plane's computer uses Bernoulli's equation to work backwards and calculate its exact airspeed. Pretty clever. So, up until now, we've been living in this ideal physics playground of the Bernoulli equation. But we all know the real world is messy. It's got friction, it's got inefficiencies, and to deal with all that stuff, we need a bigger, more powerful, and, well, more realistic equation.
So we really have two different models. On one hand, you have the ideal world of Bernoulli, which assumes mechanical energy is perfectly conserved. But then you have the real world, which is described by the general energy equation. This one acknowledges that, hey, you can add energy with things like pumps, or you can take it out with turbines. And most critically, look at that term on the end, HL, or head loss. That's friction. That's the energy that gets irreversibly lost, usually as heat, just warming up the fluid.
And believe me, this loss is very, very real. Just look at a water pump. You put energy into it to spin the shaft, but not all of that energy actually goes into moving the water. As you can see right here, in a typical case, only about 74% of the power you put in, that's the purple section, becomes useful fluid power. The other 26%? It's just lost forever to friction and heat inside the pump.
All right, so let's put all of these pieces together. We've got our basic rule of mass conservation, we've got our perfect world energy idea, and we've got our real-world losses. Let's see how all this comes together in a true marvel of engineering, a hydroelectric power plant.
It all starts here. The water in the dam's reservoir is sitting 120 meters above the turbine down below. Now, in a perfect, frictionless world, that entire 120 meters of height represents the total energy head we have to work with.
But of course, reality has to intervene. As that water comes rushing down through those enormous pipes, friction with the pipe walls literally robs the water of its energy. In this case, that head loss is equivalent to losing 35 meters of height. It's just gone, which means the turbine down at the bottom never gets to see the full 120 meters of potential. It only has 85 meters of what we call useful head left over to actually spin the blades and generate power. The rest was just wasted as heat in the pipes.
And we're still not done with the losses. The turbine and the generator themselves, they aren't perfectly efficient either. If they have a combined efficiency of, say, 80%, they can only convert 80% of that remaining energy into electricity. So after all the real-world losses, from the pipe friction and the machinery, our final power output is 66.7 megawatts.
So you see, from a simple thumb on a garden hose, all the way to a massive power-generating dam, these fundamental laws connect our world. They govern the winds in a hurricane, the lift on an airplane's wing, even the blood pumping through your own veins. The principles of energy and motion are literally everywhere. So the real question isn't if you'll see them at work, but simply, where will you spot them next?